Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very pleased that we get Fredo Durand here from MIT to talk to us after lunch. He'll promise to be really lively speaker and keep you all awake after lunch. I know it's a tough slot to put him in, but he has great stuff to talk to us about. So Fredo.
Thank you. And how do I switch back?
This one.
Okay. Ooh, and I'm still at the right resolution. Very good. Thank you, Michael. Before telling you about our research, I just want to advertise that I'm in the process of finally organizing a second symposium on computational photography and video, hopefully a year from now, maybe potentially, why not in Seattle. Nothing is in stone yet, and just if you're interested in this idea, if you have ideas on how to make it exciting and foster informal interaction, especially since we have a lot of people from both vision and graphics interested in this area, please talk to me about that. We'll also very quickly advertise work that we'll be presenting this summer, but I won't have time to talk about. We've got a paper with Kevin Chen and Sylvain Paris about more bilateral stuff, but I decided not to talk about it because my students are making fun of me each time I pronounce the word bilateral. So, but we've got a really cool new data structure that allows you to do a lot of edge-aware operations such as bilateral filtering really fast and really conveniently. And we'll also be presenting a cool optical setup that you put between your lens and your camera, and that allows you to get 4 images corresponding to 4 rings of your aperture. And once you have that information, you can do a lot of cool computational things. And finally, at Eurographics, in September, we'll be presenting a technique to magnify defocus. So if you're frustrated that you have a compact camera and that you can't have those really cool depth of field effect like Danny was mentioning, we've got a technique that tries to analyze the blur, the little bit of blur that's in there, and magnify it. And that's with Sun Min Bae. Okay, now I can give you my real talk. And the point I want to emphasize today is this idea that computation is the new optics. And what I mean by this is that we've got this really great tool to see the world better. If you look at the old ages, all we had to see the world was our naked eye. And for some people like me, the naked eye is not very good. Everyone's blurry to me right now. So, you know, mankind invented optics. And now I can put optics between my eyes and the world, and I can see the world a lot better. And finally, in recent years, we are adding computation as a new tool to allow us to see the world better. We can gather images with weird, fun, and complex sensors and optical setups, and we can throw in a lot of computation that will help us reveal things that wouldn't be visible otherwise, and then display them afterwards. And maybe a paradigmatic example of this is this work that we did with Sir Liu, Antonio Torralba, Bill Freeman, and Ted Edelson, which we call motion magnification. So what's motion magnification? It's a motion microscope. It's something where if you have a motion that's too hard to see because it's too small, like here this beam moving up and down a tiny little bit, maybe the people who are right in front of the screen can see that there are a few pixels up and down. So it's barely visible. What we can do is analyze motion, and in our papers you can find a lot of detail on how to do that robustly, and then we can re-render the sequence with the motion magnified, as you can see here. And now that motion that was invisible before is really clearly visible. So really computation put between the world and our eyes allows us to see things better. Here are other examples. In this one, we've got a grad student trying to push a really thick shelf, and grad students are not very strong. But using motion magnification, you can get a graduate student that is really strong. Babies, the baby breathing, Ted Edelson is really freaked out about his daughter. Using motion magnification, he knows that she is breathing. For some reason, it makes him feel better. I don't know if that motion really makes me feel good. And so this is all fun and entertaining, but this technique also has serious applications. We're working with Danny Freeman at MIT, who analyzes the motions inside the ear. And they're using our technique in order to better understand those things and to magnify those micro videos that they've taken of the eardrum in there. And it really allows them to understand the whole motion a lot better than just with the bare video. So this is an example of a technique where really computation reveal things that were not visible before. And in the main part of this talk, I will present a technique that combines those two tools, optics and computation, in order to gather more information about the world around us. And this is work that's mostly been done by Anat Levine, who's been mentioned earlier this morning, the postdoc at MIT, and Rob Fergus, also a postdoc at MIT now going to NYU, and Bill Freeman and myself. And this work, what we're doing is take a single image and try to get not only the RGB image like you get from a normal camera, but also get depth information. So here in this depth map, red means close, blue means far away, and everything's in between. So just to manage expectations, you see it's not a laser range scanner. It's not going to give you millimeter accurate information or whatever the correspondence of millimeter is in the imperial system. But it's giving you a pretty good depth information given that it's pretty much for free. Instead of just getting RGB, you also get that in addition. And some of you might have seen that work presented by either of the three authors, and you will see that at SIGGRAPH again. But still pay attention, because we all have a different set of slides. It's a little bit like watching The Departed after watching Infernal Affair. It's kind of the same story, but it's not exactly the same acting and the same storytelling. Okay, so what's the basic principle? Well, it's this very old idea of defocus being related to depth. So if you look at basic optics, and you have a lens here that's focusing the world on the left here onto a sensor. If a point is at the plane in focus, everything is great. All the rays converge nicely to one point on the sensor. But if you take a point that's a little farther away, those rays focus closer, and therefore the image that you get is actually a circle pretty much. And that's why you get defocus and out of focus problems. And of course, if the point is farther away, this so-called circle of confusion is going to be bigger. So the basic idea that we're certainly not the first people to have is that if we could analyze the amount of blur, the amount of defocus locally in the image, we would get depth information. Here we could say that those chips are very sharp and therefore should be close, while those beer bottles are farther away because they're more blurry. So this is a great idea, but it's not as simple as it sounds. First, if we think about it, we have one input and we're trying to get two outputs. So this is a pretty clear sign that we probably don't have information. Given one map, I want two maps. It's asking for a lot. And more precisely, the two big problems that we have are that it's not very easy to distinguish between something that's blurry and something that's blurrier, or between a sharp image of a blurry object and a blurry image of a sharp object, which one is which. And the additional goal that we have, which is also challenging, is to remove the blur. Because it might be better to have the full sharp image and to remove all those effects of depth of field. And this problem of removing the blur or deconvolution is known to be very difficult. You typically get lots of ringing artifacts. I hope you can see them. Here, for example, that's the typical output of a deconvolution algorithm. So all those problems, what can we do about it? Well, we've got two main ideas that we're going to leverage in this work. The first one is that not all random arrays of color values look like image of the world around us. And if we can characterize how the world looks like, we're inserting new information in the system, and that's going to help us with all those ambiguities and all those ill-posed problems. And this is a really powerful idea that's being more and more popular in various areas of computer vision and image processing. And the second idea is a hardware idea. It's going to be to place a mask inside the lens. And we call that coded aperture. And you see here we put this weird pattern in order to control the kind of blur that we have, to make it easier to analyze how much blur we have in various parts of the image, and also to make it easier to remove the blur. Okay, and so we're of course standing on the shoulder of giants, and there's a lot of previous work that's very inspiring for this. In particular, of course, that from Defocus by Pentland, etc. But typically they use multiple images, while we want to do it from only one image. We're certainly leveraging recent advances in blind deconvolution, and I think Aaron will talk about that later this afternoon, for shake removal. Very related to us is also wavefront coding, the idea of modifying the blur of a camera to better encode information. And this idea of using a code, a weird mask pattern, first appeared in astronomy, because in that field they don't have the choice. They can't use lenses, because lenses don't work with the wavelengths that they're interested in, well, some of the wavelengths, sorry. And so they can only use pinholes or codes. And this idea last year was also adapted to do motion, to remove motion blur by Ramesh Raskar and his colleagues using their Flutter shutter. So we're clearly building on all this work. I think what sets us apart from previous work is that we're really trying to get both that sharp, all-focus RGB image as well as the depth information, while most previous work was doing one or the other, or was using multiple images. And I must, however, say that there's also another paper by a team at Merle who does very related things from us, and they will appear as well at SIGGRAPH in the same session, so you'll be able to compare both fairly similar ideas. I'll say a little more about that later. Okay, so let's get back to our problem and formalize it a little bit more. So we're given an input image, and we can also calibrate the blur caused by the camera at different depth. So here I show it for a conventional lens. We can know both the pattern and the size for points at different depth in the image. So that's what we know to start from. And we'll call the blur kernel F, and the depth will be denoted by subscript K. And since I work with vision people, our input is going to be Y, and our output is going to be X. And so formally, we're approximating this whole defocus business by a local convolution, a local blur. So we're saying that locally in the image, what we're observing, Y, is the convolution of a sharp image. That's one thing we're interested in, with a blurring kernel. That's the calibration that we've done. And our goal is to get both the sharp image and at least the index K of that blurring kernel. And so, for example, here the Coke can is closer, so the blurring kernel is smaller, and while this beer bottle is the farther away, so the blurring kernel is going to be the biggest. So that's the problem that we're trying to solve. And so the strategy we're going to use is going to be a little bit brute force. We're going to try every single possible depth with some discretization. We're going to try to remove the blur corresponding to each depth, and locally in the image we're going to choose which one works best, pretty much. And I'll go into the detail of how that all works, but yeah, essentially we're going to try to remove the blur, assuming a given depth, and then we'll see if that gives us something reasonable or not, and we'll pick the most reasonable one to get both the depth information and the image information. So first, again, why is that difficult? Well, as I said, removing blur is a tricky business. You typically get problems here with this standard deconvolution technique that most people use, Richardson-Lucy. You get blurring artifacts and also a fair amount of noise. And of course, for the second step, deciding which blurring kernel explains best a local version of the image, we'll see that it's not very easy because once we remove the blur, some images look a lot alike. So here we try to deblur with the wrong kernel, and it's obvious that there's something wrong. That's probably not an image of the ABC letters. But those two look fairly reasonable both, and it's hard to tell which one is the best one. So that's the difficulty with that, with our problem. But let's first solve the first problem and look at deconvolution. So deconvolution is pretty bad because it's even ill-posed. There are multiple possible answers for the same question. For example, if I look at this blurry image here, which is the same as this one, it can be explained by the convolution of the same kernel with two different images. Believe it or not, but if you blur this clock image by this, you get the same thing as blurring that weird wavy image by this. And of course, all we did was to add, for Fourier fans like me, we just added a zero of the spectrum of the blurring kernel, and by definition, it gives you the same thing. And maybe a more practical symptom, as I said, is those ringing artifacts. So what can we do about that? Well, we can leverage this idea of natural images. If I ask everyone, one of those two images is an image of the real world and the other one is not, I'm hoping that everyone will answer that the right image is a natural image. And especially now that we don't really have good old TV sets, the left one is even less likely to happen. So we're good. So what is special about natural images can be really useful because we know that we should never output the image on the left. We should always output something that looks like the image on the right. So there's a whole set of possible images that we should ignore because they're not natural, and most of us are interested in manipulating real images. And so now the question is, well, it's great. We have a whole panel of humans who can tell us, so we could, hook up our algorithm to one of those Louis von Ahn internet games and ask people to click on which one is the natural and which one is not. But it'd be better to have something computational that tells us, this is more like a natural image, this is less like a natural image. And one very simple prior is just to look at the gradient of the image. This is a really well-known fact that if you look at images of the world around us, most of the derivatives are close enough to zero. So here I visualize the gradient of both my noisy thing, and you see it's white pretty much everywhere. So it means there are high gradients everywhere. Of course, given how messy it is, it's not a surprise. If you look at this image, which admittedly is an especially good case for my prior, the gradient is zero pretty much everywhere except at strong edges. And sure, this is an image of a clock. That's an easy case. But even if you look at very messy natural scenes, the derivatives are still surprisingly sparse. Okay, so this is something that we can leverage, and one very easy way to do that is to add an optimization term that says that we should prefer images where the gradient is small rather than images where the gradient is high, and we can add a penalty that is the sum of the gradient magnitudes over the image. That makes sense? So we're going to penalize high gradients. Then there are little details about how much we should penalize them, and I'll illustrate that. Naturally, when you want to do optimization and you want to penalize something, you put a quadratic cost, because quadratic is really convenient, especially in order to find a solution analytically. In our work, we found that using an exponent of 0.8 in practice works a lot better, and I'll say why. But at least the first order message is just put a penalty on the gradient magnitude. And then the way you solve your deconvolution problem is that you look for the image X that satisfies pretty much both constraints. We want it to respect the convolution equations. We want the difference between X convolved by our kernel minus the input image to be as small as possible. For that one, we just use a good old quadratic term. And in addition, we want an X that has the smallest possible sum of the gradient magnitude to the 0.8. And we put that into a big iterated, reweighted least square, and hopefully we find a solution that satisfies both terms reasonably well. And in particular, if you look at the two images that I showed earlier, hopefully the convolution term is going to be exactly the same for both those images, 0, since they both exactly respect the convolution equation. But the gradient term is going to tell us that this wavy image has way too much derivative and that the real clock image should be preferred. Okay, so how does that work? Well, on the same clock image, up you've got the input, down you've got good old Richardson-Lucy deconvolution, and you see all the ringing that I've shown earlier. Now if we add a sparse derivative prior based on the quadratic term, the one I told you is not so good, we already get something that's a lot better, much less ringing, because ringing causes high gradient, and high gradients are penalized, so it is a lot better. And then if we switch to the 0.8 exponent, we get an image that's much cleaner, even less ringing. It's very piecewise smooth. And that's why we use this exponent.
Kind of saying that there's not very many gradients, but when they are, they're sharp.
That's right. So if you look at the quadratic term, it says you should share the pain. You're going to need some gradients that are not 0, otherwise you're going to get a black, a constant image. And the quadratic term is telling you, well, put those gradients a little bit everywhere. While the 0.8 term is saying, well, make sure that only a few pixels have a high gradient and the other ones should be 0. So the way I see it is, if you want to maximize happiness on Earth, you make sure that you're always hitting the same person, so that the number of happy people is higher and there's only one person who's taking all the hit. That's the way you can see it. And actually that's one of the issues where if you see multiple versions of the talk, you'll get different explanations why that 0.8 works better. So ask the same question to Bill and to Anat and you might get a different answer. Well, slightly different. Yeah. One of them will tell you that the low values are handled differently. The other one will tell you that the high values are handled differently. Yeah, something like that. Yep.
So how did you find the 0.8?
We tried. And we tried 0.7, 0.8, 0.9. So, I mean, clearly you want it to be less than 1. Then how, what's the exact number? It's not clear. Yeah. It does okay with 0.7. It doesn't do too bad with 0.85.
Texture optimization also uses the reweighted least squares with 0.8. So
yeah, it works fine.
Legacy of.
I don't know if it's one of those constants, like the Planck constants, etc., that you need to put in there. But yeah, but it's clearly important that it's less than 1 for the very reason we just discussed, that you want to make sure only a small number of pixels have high gradients.
So you can measure it, right? I mean, it's basically the log of a measurable density.
That's right. That's right. Yeah, you can fit. You can do a regression on the log plot. Yeah. Yeah. Well, and I guess the answer to that is we haven't tried on enough images to claim that we have a low variance on our regression. But yeah. And yeah, okay, I'll stop here. It also works for beer bottles, not just for clocks. So same story here. It's a little bit better with the quadratic term and much better with the 0.8 term. Okay, so if I go back to my basic algorithm where, again, we try each candidate depth. We do the deconvolution with the calibrated kernel using that convolution with sparse prior, and we're going to choose the K for which we get the best image, and there are different ways you can measure that. In practice, we look at the deconvolution error from the first term of the optimization. Let me show you. The natural image prior essentially forces that second term to not be 0, and by measuring the deviation from 0, we get a good sense of whether we get a good answer or not. But the bad news is that when you do that with a normal lens, you don't get a lot of discrimination between various depths. So this is the center image is the correct depth. And this is with a kernel that's too small, and you see that, it doesn't look unreasonable. In practice, the energy term is saying the same thing. Both depth are a reasonably good explanation. So in order to make that better, we're going to use this coded aperture idea. We're going to put that mask inside the lens. It's going to give us a blur that has more structure. And in a sense, it's going to make it easier to distinguish between structure that comes from the natural image from structure that comes from the blurring kernel. And so if you want your own coded aperture lens, here's the assembly manual. You start with a standard lens. You need to, remove the top. Okay, then inside you've got the diaphragm. I don't know if you've ever played with that. You have the little peg here. If you move it, you can change the aperture. So that's the diaphragm of your lens. And by the way, it has all those multiple blades. In the case of that Canon lens, it's 5 blades, so that's why we had a pentagon in the blurring kernel, which you can see here. And so this is where you should put the mask, exactly at the diaphragm level, because that's where you'll exactly control the structure of the blur. So we take a little piece of cardboard, like here, with little holes, and we just put it in there. Here you go. You need a lot of Scotch tape. When I did that sequence, I was too lazy to actually do it. Rob Fergus is way better than me at carefully putting the tiny little pieces of Scotch. But then you just close back your lens. And here you go. You've got a coded aperture lens. It's a really simple modification. And with that, we're going to control the defocus pattern in order to get much better depth discrimination. So here you see your conventional lens and the coded aperture. And here you've got 2 images of a point light source. It's just a flashlight through a small hole in a piece of cardboard, and it's out of focus. And you see that with the standard lens, you get the pentagon plus some diffraction effect. With our lens, you get a really weird pattern, and that's exactly what we want. So if you look at what happens in the diagram below, we've got the mask here, and it's just hiding some of the light. And pretty much the mask that you have here is projected as the blurring kernel, and the size of that blurring kernel is going to depend on how far the point is, as I will show here. So that's for a far away point, you get a big blurring kernel, and when you get closer, it gets smaller. And with that, it's a lot easier to tell which image is the good image after deconvolution than with a standard aperture. So the first row is the images I showed earlier, where we see that the correct depth and the depth that's too close result in deblurring that's kind of reasonable in both cases. While if you use our coded aperture, you see that the deblurring gets you a very crazy thing that looks like it's full of weird ghosting artifact. So essentially our code messes up the image a lot more than a traditional lens, and that's very helpful to know by how much it's been messed up essentially. And in real images, you can really see that in highlights. Here, these are the images of the glasses, and you see here, this is pretty much our code. And essentially, those structures are harder to be confused with natural structures. That's why we can solve the ill-posed problem. Okay, so to summarize the algorithm, we take every single k, every single depth, we try to deblur using a little optimization with sparse derivative prior, and then we're going to choose for each pixel the k that minimizes the error of reconstruction. And that's what you get for this scene here in this middle depth map. So you see it's all noisy and messy, so you do the usual thing, you add a regularization term, pretty much the same kind of term that Danny was discussing, where you try to respect edges in the original image, and you get a pretty decent depth map. It's not perfect, but you get a lot of information about the scene structure. Just a word about how we came up with that particular pattern, and this is one big piece of the paper. What's the criteria we should optimize for to choose for the mask? So we generated a lot of random possible masks, and we have an analytical formula to look at, we estimate how well we can discriminate between different depths. Formally, it uses the KL divergence. Essentially, we tried all those patterns, and we chose the best one. And if you're interested in more detail, in the paper, you've got a whole Fourier analysis of how we can discriminate depth, and in particular, how that works even when you have noise, because a lot of those analyses assume you've got perfect data, and you can look exactly at the zeros of your Fourier transform. So we give you a more complete explanation, including noise and relating everything to that KL divergence. And now the results with that. So this is an input image from our camera. This is the deconvolved all-focus image. You see that the beer bottles are sharper. Close up, on top you've got the original image, below you've got the deconvolved image, and together with that we get that K number, the depth information, all from a single image. Just to show you that it's a good idea to use a coded aperture, this is what we get. Sorry, the colors are a little messed up with our lens. And then we did exactly the same thing, the same software pipeline, the same calibration with the standard lens. And this is what we're getting with a lot of ringing artifacts that are mostly due to the fact that we misidentified depth here. It's actually surprisingly bad in that case, but that's really what we're getting. Another example, so one of the co-authors is British, so that's why we have a lot of beer bottle kind of scenes. Same thing, deconvolution, you see the background is a little sharper now. This is depth estimation without regularization, depth estimation with regularization. It's not perfect. In some scenes, you're going to need a little bit of manual intervention. I think actually our regularization term could be better, because here you see that the depth information in the face area is not so bad, but I think the regularization is too strong and we're missing the head, so we can use a Scribble interface, since Anat Levin is one of the authors, in order to correct for that. And then we can play refocusing tricks, here focusing on the chips, focusing on the Coke, focusing on the beer bottles, and this is all from a single input image because we have that depth information. Here's another set of results. Depth map, you see again, it's pretty coarse. We don't make the distinction between the third character and the background because it's really standing against the walls. But still with that, we can do cool refocusing. Focusing on the first character. Oops. How did that happen? I think I crashed my keynote. Yeah, I should have used parallel. Okay, well, this was concluding my talk anyway. I think the ideas to remember here is the fact that we're coding the information with the optics, and we're decoding it with an algorithm, and to make that a lot more effective, we're using this natural image prior, which is helping us to find a good result from junk that really doesn't look like natural images. Thank you.
Thanks for... Let's see, we're running a little late, so why don't we take one or two questions while Alexei sets up.
Yes.
This is a technical detail, but when you write down gradient to the 0.8, how do you measure the gradient? Is it central differences?
Yeah, it's one of these. Actually, I don't know, honestly. Okay. But yeah, it's one of these. Yeah, I have no idea which exact kernel she's using. Yeah. That's kind of easy because we use the reweighted least square, so we just use the current gradient, and so it doesn't matter that much.
So the cardboard, doesn't it interfere with the motion of the diaphragm blades?
Oh, you can't change your aperture anymore.
Oh, okay. So it stays open.
That's right. Yeah.
Okay.
Yeah. You really.
Right. What was it?
Yeah.
Okay.
Yeah.
Okay.
And in practice, usually when I open those lenses, you also lose the ability to do autofocus because I break the little motor there, but that's because I'm brutal.
Well, you were illustrating it with an $80 lens, so...
Yeah. Oh yeah. Well, that's why we chose that one. Oops.
L series.
Now. Yes.
So how do you do the depth? Is that like a market random field thing?
So we have that data. Yeah, we have that data term, which is the deconvolution error, and then we add a regularization term, a smoothness term. That same thing as Danny. You have some Gaussian and color difference between the pixels.
Continuous optimization, not at discrete levels.
I think she's using. I think it's a discrete one in practice because we have only a small set of labels. Yeah, we have calibrated the lens at a discrete set of labels. But you could do, yeah.
Thanks a lot.
Thank you.
All right, our next speaker is Alexei Afros from Carnegie Mellon, and he's going to talk to us about using brute force. Hopefully that'll keep us awake also after lunch. Take it away.
Thank you. Thank you for inviting me. My topic is using data to brute force hard problems in computational photography. Am I too loud?
No, I just want to make sure that we get your PC2 or PC3.
Sorry about that.
I should put this farther away.
Actually, put it up here so I can't hear.
You sure?
Yeah.
All right. You want to get it though?
Is it turned on? This one.
Yes.
Thanks.
All right. All right. So brute forcing is a bad word. You know, this is what we are taught not to do in algorithm classes. And yet I will hopefully try to persuade you that maybe these are old style prejudices that we should be overcoming. But first of all, what are hard problems? Well, hard problems in our discipline, I think maybe we will agree on this, are problems that are in a way AI complete. They are problems that are not somehow can be solved by doing something with the image, some kind of image processing tricks. They are problems that rely on our knowledge about the world to interpret the image and then to modify somehow the image using our sense, our semantic understanding of the world and of what is being depicted. So this is what I mean by hard problems, kind of AI complete problems. So what is AI? Back in the old days, what is the AI dream? The AI dream is, having a computer that would answer all your questions, right? Kind of like back in, Star Trek, Captain Picard says, "Computer, what is something something?" And the computer tells you, right? And I claim that I have discovered how that computer on the Enterprise works. Okay, here's how it does it. Okay, Captain Picard says, "Computer, who is Sherlock Holmes, for example?" Okay, computer runs to the terminal, loads up Google, types in the question, hits "I feel lucky," and reads in very proper computer voice basically the first thing that is there, which chances are is not going to be something completely wrong. And in this case, for example, it's exactly the answer to your question. Okay? So this is kind of the, in my mind, essentially what we are moving to in the world of AI. The AI in the modern world that we live in is not trying to synthesize an answer to your question, but to just try to look it up, assuming that it's already there, assuming that all the questions have already been answered. You just need to look it up. And so in our world, in kind of understanding the visual world, in computer vision, computer graphics, machine learning, the main paradigm used to be, you have lots of training data, you look at all the training data together, you try to somehow squeeze out the important bits, you squeeze that data out into a model, and then from that model you can run the model and you can synthesize new stuff from that model. Yes, but that squeezing part is really, really hard, because that's where you really need to understand what are the important parts and which parts you can throw away. So that's really hard, and there are some of us who are really good at this, but I'm not. So I have a much simpler model. You don't throw anything away, and instead of understanding the world, you're essentially looking up the world. Yes, the world is still there. All your training data is around, and you're just going and trying to figure out the right answer that is close enough to what your question is, and hope that you can get at least close enough to the solution that you can afterwards kind of adjust to yourself. Okay, so that's kind of the theme that we've been working in for a while, and today I'll just talk about two projects in this broad theme. One is about inserting things into images, and the other is about removing things from images. So at the end of this talk, hopefully we'll be where we started. So these two things, cancel each other out. Okay, so so the first one, we call it photo clip art. It's joint work with a bunch of people. Jean-François Lalonde is the main author on this work, and also Derek Hoem, who has just graduated last week, and also a bunch of guys from Microsoft Cambridge, Karsten Rother, John Wynn, and Antonio Cremonesi, and this will be at SIGGRAPH this year. So say that this is a picture, who knows actually where this is a picture of? Yes, it's a modern day picture of the Abbey Road, kind of looking lonely, there's something missing here, there's just not enough going on. So what if we want to add something to this scene, okay? So what can we do? Well, one thing we can do is we can fly to London, okay? We can calibrate our camera. We can, take a picture of a glossy sphere of one of Paul Debevic's collection spheres, put a big lawn ornament there, take a picture, get an environment map, and finally get yourself a nice-looking bunny. Okay? Great. But, that's a lot of effort for questionable result. What else can you, well, if you want to do something just really, really fast, then you can just go to, PowerPoint clip art library and you just pick up a few kind of people standing around, and you get yourself a really fast mock-up. So what we want to do is we want to do something in between these two extremes. We want something that is so on one side you have very realistic, but very time-consuming. On the other hand, cheap and intuitive, but doesn't look that great. So we want something in the middle, and that's we call this photo clip art. So it's clip art, but using real photos. And the hope is to try to be as photorealistic as we can. We don't always succeed, but at least that's the direction we want to go into. So there are two key kind of insights that make the problem doable for us. So one is that inserting the car into this scene is, I claim, an impossible task, just from seeing, just these two images. Because there's just a lot of things that can go wrong, right? The lighting would be wrong, the shadow could be wrong, the camera view, the camera pose could be wrong. So this is not the problem that we want to solve. We want to solve a more general problem, inserting a car into a particular scene. Okay? So now we have a set of different cars, and what we need to figure out is which of these cars would fit well into the scene. And once we do that, then we just copy it over, and we get something that is actually a solvable problem, we claim. The other issue, well, so basically what in fact we are doing is the processing is given lots and lots of data in your data set. We are just going to, and the new image, we are just going to resort the data to make sure that the objects that are likely to fit in well visually into the scene are at the top of our list. And then we still have a user who can choose which of these clip art thingies would he wants to put in there. Okay? So basically all we are doing is we are doing a reordering. Essentially like Google. Google, you have all the web pages in the world, and when you search for something, it will resort all the pages in the world and give you a couple of screenfuls of the top things that Google thinks you meant. So we are doing kind of the same thing. Of all the people in our data set, we are giving you a few screenfuls of people that we think will fit in well in here. Okay? The second insight is to what we are going to do in dealing with adding things in objects into images is to forget that it's an image. Okay, we don't want to deal with it as an image like in a Photoshop way. We want to deal with this as a scene. Okay, so we try to as much as we can, given that it is only a single image, we try to manipulate it as if it was in fact in the three-dimensional world, not in the two-dimensional plane of the scene. So the manipulations that we want to do them in the space of a scene, not in the space of the image. Okay? So there is a lot of prior work. Just two kind of broad categories is, there has been some work in single view 3D reasoning, starting from a very influential work, Durand to the picture work, and going through some photo editing in 3D that Fredo and company did, and our pop-up stuff, of basically taking this line that you shouldn't edit images, you should edit and you should look at scenes that these images represent. And second part is that has really been very influential to us is this beginning of data-driven approaches applied to image collections. And there has been some really cool work on semantic photosynthesis and the content-based synthesis, which is basically trying to synthesize images from relatively large, but not too large, collections of other images, and of course the phototourism work, which is kind of a more localized way of trying to create something from a collection of images of a particular physical space. Okay, so and these are actually these works influenced both of the works that I'm going to present here. So what is the outline? The outline is we are going to do two things. First, in the pre-processing step, we're going to take our big database and we're going to annotate every object in a database with some properties that we will need later for inserting the object into a novel scene. Okay, so first we do pre-processing, and second we'll do object assertion. So first of all, the database is very important. How do you get all the data? Luckily, there is the Label Me dataset from MIT, which lets you download a huge amount of reasonably segmented objects for kind of standard outdoor, mostly urban type scenes. Okay, so this is the data set we are using, and it's growing every day, and it's been really, really helpful for us. The data set is we need to clean it up a little bit and pre-process it. So the data set we pick a number of categories for which we want to use. Usually it's categories which are well represented in the data set, and also categories that happen outdoors. And then for every category we also have subcategories. And how do we get subcategories? Well, sometimes they're annotated, like these cars with orientations. And when they are not annotated, we are doing simple clusterings to get subcategories. Okay? But now for every object we want to annotate the object with its properties, its geometric properties, and its photometric properties. So we want to know, how high was the camera when the object was taken, what was the orientation of the camera, and what was the kind of rough lighting of that object. Okay, so first of all, the camera parameters, camera viewpoints, obviously very important. On a 2D image, you can have, a car and a person could appear completely out of proportion to each other. But when you look at it in 3D, you realize that actually, they are of comparable heights. And what we are going to do is we're going to model this interaction between the 3D world to the 2D image with very simple two-parameter setup, the camera height and the camera orientation, one angle, just basically the horizon position. We are assuming that the camera is not doing that, and we are assuming that all the objects are on the flat plane. And this comes from some of the previous work that we have done. Turns out that statistically, almost all the pictures that you will find on the net are it's sufficient to model it like this. Okay, so now we want to estimate camera parameters for all the images. How do we do this? Well, here is our approach. We start with something that we know. We can go to NIST or whatever health, what is it? The Center for Health Statistics, and we can figure out the average height of a particular person and the variance. Okay. So now we go to Label Me. where there is some people labeled, okay? We know what the average person height should be on average, and then it's a pretty simple kind of a least squares problem to estimate the camera parameters given that we know are roughly the heights of the people. Okay, great. So now we have the camera parameters for this particular image. Okay, now we can do the same for another image where there are some people. Okay, so we can, from those people, we can estimate the camera parameters, but then there are also another object, say car. Okay, and there's a couple of cars. So then we can use the figured out camera parameters to estimate the rough height distribution of this new class, cars. Okay, so now that we have estimated the cars, we go to an image which has no people. Okay, we can still estimate the camera parameters, and then we see there is a new class called truck, and great, now we can estimate the camera the height distribution of the truck as well. So there's kind of iterative process where we slowly labeling more and more of the data. Now, clearly here, we need to have at least something labeled. If it's an empty image, we will not be able to estimate anything, but this is okay because, after all, this is a labeled data set, and that's what we are after anyway. So, so one nice thing that we have, so not only do we have camera parameter estimates for all the images in the data set, but we also have physical height estimates for all objects. 3D height for all the objects in our data sets. So here is an example of a photograph, and these are all the labeled people, and these are their heights in pixels, and these are their heights in meter or centimeters. And you can see that the right things happen, that they all get to be on the same scale relatively, as well as actually absolute scale as well. Okay. Now bad things happen if your floor is not completely flat, and if people stand on sidewalks, then you get a little bit of off. But in general, it's actually doing pretty well. Here are some statistics. These are some kind of average images of the different objects that we have discovered heights of. And the interesting thing is that for man, woman, you can look up these numbers. Especially for parking meters and fire hydrants in Boston, you could actually look up what is the official height of these, and we are doing like within 2 millimeters, I think, of the actual mean. So we are on average doing well. So for a given image, we might be wrong, but on average, we're estimating these things pretty well. Okay. So now that we have that, geometry is still not enough, because you might have, okay, geometry, but then the photometry will kill you, because somehow things just don't look right in a particular image. And if you look at, for example, this car, where was it taken from? Well, it was taken from a day that was much more sunny, and you have a little bit of, blue being reflected by the car, and in this image is more overcast, so it kind of looks a bit weird. So what we would rather have is find images which have relatively similar weather conditions, and then steal, a car from somewhere there. And hopefully that will look better. Okay, so for that we need to somehow estimate the rough illumination of a particular scene. But again, from a single image, that's really, really hard thing to do. In fact, impossible, once again, thing to do. There has been, a bunch of ways to approximate it, and this is also what we do. We're trying to see how can we approximate what we call it illumination context of the image. So we had some work in geometric context. This is illumination context. Okay? And what we do is basically we're saying we're going to make an environment map, and it's going to be really, really coarse. It's going to have essentially, instead of environment map having millions of pixels, we'll have basically 3, not pixels, but 3 bins. We're going to have a bin for ground, a bin for sky, and a bin for everything that's vertical. Okay? So we have an environment, but it's going to be very, very coarsely represented. And it's also going to be low dynamic range, because of course we have only a low dynamic range image. But this is okay, because we'll never use this environment map to synthesize anything. We're only going to use it for matching. So it's going to be okay, because all the bad things that happen when you go to LDR, the same bad things will happen. So matching, chances are, will not be disturbed too much. So how do we do this? Well, we're using the pop-up stuff to classify the image into the 3 surfaces, and then basically we are computing some color statistics of each region separately, and that's our illumination context. Okay. that's the illumination context, and here is an example of some retrieval results, okay? And the retrieval results are, so this is kind of your day overcast sky, and here are some examples. This is kind of your morning scene, and it's kind of nice that what you get is you get a bunch of images that do look like they're morning images. And here is your kind of sunny noon image, and then you get something that's similar. Again, notice that this really, it works not because this illumination context is super clever. It works because we have tons of images. And chances are, when you have lots of images, you'll find something that looks close enough. Okay? So now that we have the estimate of the lighting, there is a few other estimates that we can do. The local context, so for example, this guy doesn't very much fit well because its local context is completely different, whereas this woman fits much better because, she was taken from an image that was matched much better. So we have another term which basically matches the kind of surrounding pixels. Also, how good is the segmentation? We want good segmentations and we don't want bad segmentations. Unfortunately, label me, lazy users do things like this, and the not so lazy users, put much more points. And there's, the simple way to do this is just say, we want to rank higher objects that have more clicks on them than less. That's a simple thing. Blur, we want to make sure that kind of the blur level is similar, all the reasonable things. So now we have computed a whole bunch of statistics for every one of our objects. So we have computed, the camera height, the object height, the illumination context, the local context, the segmentation quality, the blur, etc. So now we have annotated the label me dataset with all this stuff. Now we are ready to do insertion. Okay? And how do we do it? Well, the segmentations are still polygonal segmentations, okay? So the main problem for us is going to be that, you are going to see some nasty artifacts around the edges, so we need to clean that up. And the way we clean it up, something like this, is of course using a lot of the literature from segmentation and blending, and I'm going to skip that part just to say that we had to develop some new methods. We couldn't just use stuff out of the box, but we had to, work a little bit to get it to work because our problem is a little bit different. We don't allow interaction on this stage, so we have to really do it in one shot. So, it has to be a little bit more certain about what it's doing, but you can read the paper to see what we did there. And finally, very, very important, shadows. Shadows are extremely important. You take away the shadow and an object just appears to be floating. Okay? But the thing is that creating synthetic shadows is really, really hard. We tried that. We need you need to really have a 3D model of the object. You need to have a really good environment map, and we never got it to look good enough. But then we thought, well, we can keep doing the data-driven stuff. So instead of creating shadows, we're going to just transfer shadows. And the key here is that even though shadows themselves are important, turns out that their orientation is really not that important in the grand scheme of things. So what we're going to do is we're going to just steal the shadow from where the object headed before. So here is a car from its original image. We have detected some very poor man's shadow detection. Now we have also estimated the contact points with the ground from some learning, and we have kind of cleaned up the shadow to cling to the contact points. And here is the same car in a new photo where we want to place it, and it doesn't have a shadow yet. And here is our shadow that we have estimated, and we just painted in, just blacken the right place in the new image. And then when we add the two together, magically we have something that really doesn't look so bad. Even though the shadow might be of completely different orientation because the sun could be in a different direction, it doesn't seem to matter that much. Okay? So finally we have the user interface, which lets us oh boy, all right, let me just start again. Apple products. So here is the user interface, and here we have all the objects, and here we have the subcategories for objects, and this is our sorting panel. These are the kind of the top results. Okay, so we can given an image, it resorts, and now you see that we have kind of a 3D interaction in this space, right? As we move the mouse back and forth, we have the object becoming smaller and bigger because we are in fact editing in the sense of the scene, not in the space of the image. Okay? Or you can first specify the position where you want to put the object, use that as your local context, and then it will sort the objects that that will most likely fit it, and then one click and it does all the blending and cutting and all that stuff. Okay? So that. And here are some results. So here is an input image, and we have synthesized an accident. Turns out that this is Antonio Torralba, who was in the Label Me dataset, and who is the creator of the dataset. We didn't know, but he came and said, "Oh, that's me." Here is another example of adding cars to an image. Here's a painting, and we add couple of objects there, and it's really simple to play around with this kind of interface. You really don't need to be an artist. You just kind of click and drag and just one. Sometimes it doesn't quite work right. So issues may arise in blending and segmentation, but then you can still you can just redo it and put somebody else. So there is an interaction there. Here's an example of the new Gates building. This is just a rendering, and you have all these white ghosts that the renderers, the architects put there to show that it's very exciting and livable space, but it doesn't look very exciting and livable. We think that we can do a much better job making it more lively. But it does, of course, fail in a number of cases. Sometimes objects just don't fit in, so you have kind of blending artifacts, segmentation artifacts. Shadows sometimes don't transfer well because the shadow detection is still a very hard problem. And sometimes it's just that you don't have the right types of objects in your data set. So for example, here, this kind of a weird night scene with snow, we just really did not have any data in Label Me to find something that would match. So here we're adding the best matching objects, but they obviously don't match well enough. So to conclude this part, it's basically two things: using data and thinking about it in 3D. And of course, plenty of challenges remain, but the cool thing is that many of them are solvable by like in the recipe package, just add data, and a lot of the problems will go away. Just because the more data you have, the more chance that you'll have that the matchers will find the right thing. Yes?
We're about out of time.
All right.
So if you're going to do the second part, you want to just give us the punchline, and then during the break we can have
all right.
This can be one of some demos.
All right, sure. I can. This is. So how quick of a?
Take 5.
Oh, I can do. Easy. All right. So basically, this is another problem, which is the opposite of the previous one. We want to fill in holes in images, and this is work with James Hayes, also at SIGGRAPH. And so basically, the idea is that we have a car, we want to remove it, and we want to basically put something in that would make sense. Okay, and if you look at all the literature, all this, textures, synthesis, silly things, it just doesn't work. Horrible. I don't know. And the reason, what you want is we want this, but this is a semantic idea, right? You know that you want a piece of the road there, and how do we tell the computer to think semantically? And basically, the idea is this, right? We tell the computer by having tons and tons of data to figure out something that is close enough and transfer the semantic knowledge into the new image. Okay? So we have 2.3 million images from Flickr, and basically here is the approach. We represent the image in a low frequency representation. We use the gist of Oliva and Torralba, and we get some nearest neighbors, and then notice that several of them, about half of them essentially, are semantically the same scene. Okay, so we can try to see if we can steal content from those scenes and to fill in our hole. For example, for this image, let's see, can we use this image? Well, we can take the local context, search around, see if we can find a good match, and we do it for many many of them, and we do the typical, standard cutting and blending, and then they give the user about 20 resulting synthetic images, and I'll just show you some of them. And some of them are better than others, but out of those 20, chances are you can find stuff that you like, and they're also going to be kind of different. And so this one is the one I kind of like. Okay, so here I'll just show you some other results. I don't like this. Let's get rid of it. Put some. So what did it do? These are the nearest neighbors. This is the one it liked best. Boom. Blending, cutting, done. Here is my favorite. Get rid of this wall. Put something else in. These are the matches. This is what it did. Okay, crane, etc. So to go to the punchline, the punchline is that we did a quantitative evaluation. We actually measured how well we are doing. Okay, so we compared ourselves to Cremonese. It's a little bit cheating because we are, here we choose what we want to pick out of the 20 examples. In Cremonese, whatever you change the parameters, it's all pretty much the same. But here is the setup. This is an image. Is it fake or is it real? That's what we ask people. Who thinks it's fake and who thinks it's real? Fake? All right. Real? Well, I think a third thinks it's real. It's actually fake. This is the real one. And here is the exciting part. Okay. So this is maximum response time, and this is how many percentage of images are labeled fake. Okay. So for Cremonese, they got it. They got it 90% of the time. They think it's fake. Okay. For our algorithm, they decided that about 2/3 of the time they caught us. Okay. At the level of thinking that about 13% of the pictures that were real, they thought they were fake. So they were kind of overshooting a bit. But the interesting thing is about 10-second line. Okay, so notice the longer they think, the more skeptical they become. But 10 seconds is basically kind of the first looking at it before you kind of get paranoid and start searching for where there could be an error. And here we're doing really, really well. We're basically fooling them 60% of the time, or even more, on kind of a first glance test. Whereas Cremonese and basically all the texture synthesis stuff, it's much worse. Okay, so this is kind of promising. That means that if they don't expect to be fooled, maybe we can fool them. And finally, what is it? What's the trick here? The trick here is not that the gist is super cool and much better than everything else. The trick is again data. If we are looking for some match and we don't have enough data, then distance metric is very, very important to us. But if we have tons of data, it really doesn't matter what your distance metric is. Anything that's close enough will be good. If the nearest neighbor could use just any old metric, and you'll find something that's similar to you because you have lots and lots of data. And there is advertising a paper by Antonio Torralba and Rob Fergus and Bill who showed that they have 70 million images. And they are also seeing this kind of pattern that as soon as you get tons of data, suddenly this kind of a quantity becomes quality and you start seeing exciting stuff. So in conclusion, there is plenty of information in a single image, but to fish it out, you need to use lots of data. Okay?
Thank you. Let's do one question. Go ahead.
I have, my question is what application you think it's useful for, and I might have a follow-up question depending on your answer.
Which part? Oh, so...
For the second part.
The second part is basically, I think that's just, it's a little cute graphics demo, but I think really it's in the main benefit will be in computer vision, because filling in holes, okay, that's cute, but really what we can do is we can steal not just image pixels, but we can steal labels, and we can steal meaning and knowledge, and I think that's where the exciting stuff is going to happen, kind of really doing example-based image understanding. I think that's going to be a really cool thing, and that's what we are working towards now. But for filling in holes, I don't know. People still think that texture synthesis is exciting, so they might find something exciting about it.
No, thanks a lot. Thanks a lot, Alexei. So.